Now that we have gone through the process of partial fraction decomposition, I want to talk about a couple of unique cases and some types of different strategies we're going to have to employ depending on what our original fraction looks like. So I've written notes for all three of these partial fraction decomposition cases to be mindful of. Um, the first one that I want to highlight is this first note about if the degree, excuse me, actually I want to start here. If we see that we have repeated factors in the denominator, like x plus 3 in this case, cubed is our original fraction, what we're going to want to make sure that we do is when we're writing our fractions out, we're going to want to have one fraction for every consecutive power of that factor. We don't want to just write x plus 3 plus another just x plus 3. We have to make sure that we have a subsequent power for each of those so that when we add up all three of our fractions back together, we get the original fraction as it was. So let's go ahead and model something like that. So let's take a look at this first problem. So the very first thing we always do when we do partial fraction decomposition is to factor our denominator here. And I see that this has a common factor of x, and we're left with x squared minus 2x plus 1 once we factored out that x. And this can be written as x minus 1 times x minus 1, which can also be written as x minus 1 squared. So what we're going to do now is we're going to then go ahead and create three different fractions here. We know it's going to be the sum of three fractions. Well, what are in their denominators? First, the first denominator is going to have our first factor x. Our second fraction is going to have x minus 1. And our third fraction, instead of just another x minus 1, we want to make sure that we have the higher degree power for this one, x minus 1 to the second power. And again, this is to ensure that when we do the same process of using a system of equations to solve for our numerators, a, b, and c, that we make sure that we get the original fraction as it was, okay? So now that we have this factored out and split up into our fractions, our next step is to multiply everything by our LCD, which means on our left side, we just get our numerator. On our right side, we're going to get a times. If we multiply this first fraction by our LCD here, we're going to get x minus 1 squared as what's left over after we divide out our x's. Next, we're going to multiply b times b over x minus 1 by our LCD, and we're left with the x and one additional x minus 1 factor. And then finally, when we divide our last fraction here by our LCD, our x minus 1 squareds are going to divide out, but you still will have that x term left over. So we'll go ahead and multiply those. Now from here, it's going to be a little bit of just distributing and basic algebra. So x squared minus 2x plus 1 plus bx squared minus bx plus cx. And let's go ahead and distribute that a out in front as well. And this is bx squared minus bx plus cx. All right. So again, I want to highlight that this is all equal to this. So in order for us to do this, we want to kind of start grouping together our similar terms. First, let's start with grouping together our x squared terms, okay? So we've got a plus b, and this x squared left over here. And that's got to be equal to this 3x squared. So we can then say a plus b is equal to 3. We know that this coefficient here must be equal to this coefficient there. Next up, let's group together all of our x terms. So we've got negative 2ax minus bx plus cx. That has to be equal to negative x. So let's write that. So we've got negative 2a minus b plus c with that x factored out. So negative 2a minus b plus c, that has to be equal to negative 1 because that's a coefficient in front of the x. Finally, let's go ahead and group together. Well, the only thing to group is this a. We know that has to be equal to 5. So let's write that as its own line here in our system. A is equal to 5, which makes our life a whole lot easier now when we need to solve this system here. Because we know a is already equal to 5. We know that 5 plus b is equal to 3. B is equal to negative 2. And the only thing left over is to solve for our c. So -2 times 5 minus -2 plus c is equal to -1. And that means c should be equal to 7. So now that we have our values for a, b, and c, let's go ahead and write our original decomposition. So here, in place of a, b, and c, we know what they're equal to. A is 5, b is equal to -2, and c is equal to 7. So there is our decomposition. Okay, let's go ahead and do another example. This time I want to highlight here that this particular problem, number 2, is highlighting this rule or this note up here, that whenever we have a quadratic factor in the denominator, that the decomposition must include an ax plus b, or in other words, a linear factor in the numerator, or a numerator must be 1 degree less. And this happens when our denominator is a quadratic factor that can't be factored any further. To be clear, this does not include what we did in this previous problem. So this x minus 1 squared, we don't consider that a non-factorable quadratic factor. We look at that as a repeated linear factor. So don't confuse the two. But let's take a look at number 2, because I think that actually seeing the factor will hopefully distinguish this. So this here, I want to go ahead and factor that denominator. So this is x squared plus 3x minus 1. And then the denominator here, well, I notice I can factor this by grouping. So I'm going to write x squared, x plus 1, plus 2 times x plus 1, which then allows me to rewrite this as the following. We can say, all right, well, x squared over plus 3x minus 1. This is going to be factored as x squared plus 2 times x plus 1. And if I split up my fractions here, let's write this as a over, let's do the linear factor first, x plus 1, and then b here as x squared plus 2. Now, you might be asking, well, what if I switch them around? What if I had x squared plus 2 in the front? Oh, I apologize. Let me take a step back. I should mention here, sorry, since this factor here, or this denominator is quadratic, I need to make sure that my numerator here is written as bx plus c. Since my denominator is a non-factorable quadratic factor, and I should say I can't factor it with real numbers, then my numerator has to be 1 degree less. It has to be linear. If you had put x squared plus 2 first and made this as x plus 1, that's fine. You would then just express this numerator as ax plus b, and this over here as the 1 over x plus 1 as c. Both of these are totally fine. They will give you different values of a, b, and c when you solve, but your final decomposition will be exactly the same. So it will not make a difference. So I'm going to just go ahead and continue with the way I've written it. So here, we're going to multiply both sides by the denominator. I'm going to move a little bit more quickly now since we've done this a few times. This would be a times x squared plus 2 plus bx plus c. Be careful with your parentheses because we're going to have to multiply that by x plus 1 in a moment. Let's distribute and multiply. And this would be bx squared plus bx plus cx plus c. And if we group together our terms, we're going to say, all right, we have a plus b times x squared. And we know that this has to be equal to x squared. We know, let me do a different color here, 2a, excuse me, let's not jump to the 2a just yet. bx plus cx, or b plus c times the quantity x, has to be equal to 3x. And then finally, these constants, 2a and c, have to be equal to -1. So from here, we can go ahead and write our system as a plus b is equal to 1, because that's a coefficient in front of the x squared. B plus c has to be equal to 3. 2a plus c has to be equal to -1. And you can solve this in whichever method that you want. I'm going to have you pause and solve this on your own. But what you should get as your final answer, as your decomposition, should be the following. This should result in a is equal to -1 if you did it the way I did. C is equal to +1. So this should be -1 over x plus 1 plus 2x plus 1 over x squared plus 2. And there's your decomposition there. Okay. Now, the final case that I want to discuss is a partial fraction decomposition in which the degree of your numerator must be greater than the degree of the denominator. When that happens, all you're going to want to do first is just long divide and then do the partial fraction decomposition to the remainder only. So I won't do this entire problem because I want to make sure that you have some problems for you to practice on your own. But if I'm doing the long division here first, just to really quickly show you this, this would be x squared plus 3x minus 4 would go into this polynomial x times, which would make this. And when I subtract those rows, I'm left with negative x squared plus 3x plus 1. So then I'm going to multiply this out here by -1. And when I subtract that, I'm left with, what is that? 6x minus 3. That's your remainder. So this here, this rational expression is equivalent to x minus 1 plus 6x minus 3 over x squared plus 3x minus 4. This is what we are going to use for our partial fraction decomposition. So you're going to do the partial fraction decomposition to this only. And this isn't too bad. This is actually on par with some of the easier ones we'll do in this section. But just to give you a sense, your final answer should look like the following. We should still have that x minus 1 as our answer. But once we have done our partial fraction decomposition to this part, you should get 27 over 5 times x plus 4 plus 3 over 5 times x minus 1. So try that problem on your own and check your answer with what I have here, but this is hopefully what you get.